Hello everyone, welcome to Module 8, Lesson 4 of Mastering Ethereum. Today we are going to explore some fascinating strategies for improving the performance of decentralized applications. If you ever felt that your DApp could be snappier or even more efficient, this session is for you. We'll cover a range of topics including user behavior analytics, front-end optimization, and the use of advanced layer 2 scaling solutions. So let's dive right in. Let us see factors affecting DApp performance. There are on-chain factors and off-chain factors. On-chain factors include gas costs, which directly affect user fees, while transaction speed influences the user's perception of responsiveness. Slow transactions can create a frustrating user experience. Off-chain factors play a crucial role in DApp performance. A sluggish or unresponsive UI can lead to user frustration and abandonment. Data handling, including loading times and data retrieval efficiency, is also critical. Balancing on-chain factors and off-chain factors is important for a seamless user experience. Striking a balance between these aspects ensures efficient execution, reduced cost, and enhances user experience. Here are some ways of optimizing your smart contracts. Efficient smart contract design is crucial for DApp performance. By reducing gas costs and optimizing execution, developers can create more user-friendly and cost-effective applications. Optimized contracts improve user experience and ensure smooth operation on the blockchain. Gas cost reduction is of paramount importance for smart contract optimization. Techniques include minimizing storage operations, avoiding unnecessary loops, and utilizing efficient data structures. These practices enhance contract efficiency and reduce user fees. Example is a token transfer. A token transfer function is a common example where optimization is vital. By using efficient data structures and minimizing storage interactions, developers can reduce gas consumption and improve transaction speed, making transfers faster and more cost effective for users. Let's examine a basic token transfer function, a common operation in DApps. This function facilitates transferring tokens between addresses, and its efficiency is crucial for performance. By employing optimizations, we can reduce gas costs and improve transaction speeds. We can achieve this by minimizing storage interaction and avoiding unnecessary computations. The optimized version will result in more efficient and user-friendly approach. The Solidity smart contract for token includes a mapping called balances that associates addresses with token balances. The transfer function allows the transfer of tokens from the sender's address to the specified recipient, ensuring that the sender has sufficient balance before proceeding with the transfer. If the sender has enough tokens, the specified amount is deducted from the balances and is added to the recipient's balance. This function helps manage the distribution of tokens within the decentralized application in an efficient and user-friendly way. Switching gears, let's talk about gas optimization techniques. Think of gas optimization like optimizing the fuel efficiency of a car. You want to ensure it runs as far as possible on as little fuel as possible. Techniques like avoiding redundant computations and using efficient data structures can significantly reduce gas costs, making your smart contract more economical. One of the most basic gas optimization techniques involves minimizing redundant computations. This can be achieved by storing immediate results and using them instead of recalculating them every time. This simple strategy can significantly reduce gas costs. In a token contract, mapping allows direct access to specific balances based on addresses, whereas an array would require iterating through all elements to find the desired address. This optimization makes access more faster and reduces gas costs. Layer 2 solutions for scalability. These are akin to setting up an express lane on a busy highway. Instead of processing every transaction on the main chain, Layer 2 solutions process transactions off chain and then bundle them off for validation on the main chain. This dramatically improves transaction speeds and reduces costs. Optimistic rollups are common Layer 2 scaling solutions that batch transactions off chain and submit them to the main chain for validation. This approach significantly reduces gas costs and improves transaction speeds. Zero-knowledge rollups use cryptographic proofs to verify transactions without revealing their details. They offer even greater scalability and privacy as they bundle multiple transactions into a single proof for efficient validation. Plasma is a layer 2 scaling solution that uses a sidechain to process transactions off-chain. It utilizes a smart contract on the main chain for security and finality. Plasma is well suited for applications requiring high transaction throughput and low latency. Let us now look into an example of integrating optimistic rollups. The pseudocode provided is outlining the integration of optimistic rollups into a smart contract, specifically for depositing and withdrawing assets between layer 2 and the main chain. The deposit function is a publicly accessible function that executes the logic for depositing assets from the main chain to layer 2. When a user initiates a deposit, the function processes the transfer of assets, potentially updating the user's balance on layer 2 based on the amount deposited. The function is crucial for moving assets efficiently and cost effectively between the main chain and the layer 2 solution like optimistic rollups. The withdraw function also is public and is responsible for logic of withdrawing assets from layer 2 back to the main chain. Users may trigger this function to transfer their assets back to the main chain, potentially updating their balances accordingly. These functions essentially serve as the interface between smart contract and the layer 2 solution, enabling seamless movement of assets. The actual logic within these functions would improve handling the asset transfer securely, updating balances, and ensuring integrity of the transactions happening between the main chain and layer 2 solutions. Let us now look into importance of caching. Caching is crucial for boosting DApp performance. It reduces server load and minimizes network requests by storing frequently accessed data locally. Caching minimizes response times, enhancing the user experience. It is much like how a restaurant keeps popular ingredients prepped up and ready to go. Efficient caching strategies accelerate data retrieval and minimize latency. This improves application responsiveness, leading to faster loading times and smoother interaction for users. Here are some examples of caching techniques. HTTP caching utilizes headers to control how browsers and intermediate servers store responses. In-memory caching stores data in server's memory, offering fast access but limited storage capacity. Caching techniques like these optimize resource utilization and improve performance. By reducing server load and minimizing network requests, caching enhances overall efficiency and user satisfaction. Here is an example code snippet of implementing caching in React. The useEffect hook is employed to perform side effects in functional components. It is used to execute the data fetching and caching logic. Inside the useEffect block, an asynchronous function fetch data is defined to handle data retrieval and caching. The function first attempts to retrieve cached data from the local storage using local storage.getItem API data. If the cached data exists, it is passed and set as the component data using setData. If the cache data is not available, a network request is then made to fetch the fresh data from api.example.com. Once the response is obtained, the data is parsed and stored in the local storage using local storage.setItem. Subsequently, the component's data is updated with the fetch data using setData data. The fetch data function is invoked immediately, ensuring that the data fetching and caching process initiate when the component mounts. Overall, this code effectively combines asynchronous data fetching and caching to improve the performance of the React application. By storing retrieved data in the local storage, subsequent requests for the same data can be fulfilled from the cache, reducing the need for repeated network requests and enhancing the overall user experience. Another key component for improving DApp performance is reducing network latency. High latency can significantly affect user experience. Users may experience slow loading time, delay in interactions, and even failed transactions. Minimizing latency is essential for smooth and responsive DApp. Several techniques can be employed to reduce network latency. Delivery networks (CDNs) distribute static assets across multiple locations, allowing users to access content from servers closer to them. Efficient data fetching strategies such as using smaller payloads or compressing data can also contribute to lower latency. By using a CDN, reapps can serve static content such as images, CSS files, and JavaScript libraries from servers closer to users. This reduces the distance data needs to travel, resulting in faster loading times and improved user experience. Content delivery networks or CDNs distribute static assets like images, CSS files, and JavaScript libraries across multiple locations, allowing users to access content from servers closer to them. This reduces the distance data needs to travel, resulting in faster loading times and improved user experience. The benefits of using a CDN include faster load time, improved scalability, and reduced server load. Configuring a CDN in React application is straightforward. You simply need to update the URLs of the static assets to point to the CDN's net servers. This can be done in your HTML files or by using CDN provider's library. The example code demonstrates using CDN for static assets. CDN provides clusters like Cloudflare, Fastly, and AWS CloudFront offer various features, including caching, compression, and security. Choose a CDN that suits your needs and integrate it to your DApp for enhanced performance and scalability. User feedback is essential for improving DApp performance. Users appreciate being informed about the status of their actions. Clear feedback and mechanisms improve the overall usability and satisfaction with a DApp. Loading indicators such as spinners or progress bars keep users informed during long operations. Success messages confirm successful actions. Error messages provide information about issues, helping users understand and resolve problems. Examples include using a loading spinner. A loading spinner is a visual indicator that lets users know a process is ongoing. It provides a sense of process and prevents users from feeling like the application is frozen. Implementing a loading spinner in React is straightforward. Let us look into this through this example code snippet. This code defines a loading spinner component in React, which represents a spinning circle to indicate the loading process. The loadingspinner.js file contains the JavaScript for loading spinner component. It imports React and associated CSS file for the spinner styling. The loading spinner function is a React functional component that returns a spinning circle element. This element is defined using the div with the class name spinner. The loadingspinner.css file has CSS code which provides styles for the spinner component. The .spinner class defines the visual properties of the spinner. It sets the border to create the circular shape. The animation property specifies the spinner animation with a duration of 1 second, a linear timing function, and an infinite loop. The add keyframes rule is used to define the spin animation, which rotates the spinner from 0 to 360 degrees, creating the spinning effect. When incorporated into the React application, the loading spinner component can be employed to visually indicate the ongoing processes, thereby enhancing user experience and improving feedback during loading operations. Asynchronous operations are vital for smooth user experience. They prevent applications from freezing during long tasks, such as data fetching. Properly managing these operations is crucial for maintaining responsiveness and performance. Async/await and promises are powerful tools for handling asynchronous operations. They simplify code structure, making it easier to manage callbacks and errors. These techniques enable developers to write clean and efficient asynchronous code. Fetching data asynchronously is a common task in DApp. It ensures that the UI remains responsive while waiting for data to load. React provides built-in mechanisms for handling asynchronous operations, simplifying the process of fetching data and updating the application state. Let us now look into an example of fetching data asynchronously using this provided code snippet. The data fetcher component in React is designed to asynchronously retrieve data from an API and render it in the user interface. The component begins by importing the necessary modules React, useState, and useEffect are imported from the React package to manage state and side effect within the component. Within the function body, the useState hook is utilized to declare a state variable data and its corresponding updater function setData. The initial value of data is set to null. The useEffect hook is employed to execute the data fetching logic. It specifies a callback function that initiates an asynchronous data retrieval operation using the fetch API to access api.example.com. Upon the response, the JSON data is extracted and stored in the data state using the setData function. Within the component's return statement, a conditional rendering logic presents the fetched data in the pre-formatted manner using the pre-tag if it exists. If data is not yet available, a loading message is displayed. This conditional rendering ensures that users receive appropriate feedback while the data is being fetched. Finally, the data fetcher component is exported, making it available for use in other parts of the application. Monitoring and analytics are crucial for DApp performance improvement. They provide valuable data about user behavior, performance bottlenecks, and potential issues. By analyzing this data, developers can identify areas for optimization and enhance user experience. Several tools are available for monitoring and analytics. Google Analytics provides comprehensive website data, including page views, user engagement, and traffic sources. Sentry monitors for errors and exceptions in applications provide detailed insights into crashes and performance issues. Examples include Google Analytics. Integrating Google Analytics in React applications is straightforward. By installing the Google Analytics library and providing the tracking ID, developers can capture user interaction page views and other valuable data. This data can then be used to analyze user behavior and identify areas for improvement. Google Analytics provides comprehensive data about user interaction, page views, traffic sources, and other valuable insights. This information allows you to identify bottlenecks, optimize your DApp, and enhance the user experience. Let us now look into integrating Google Analytics using this provided code snippet. It utilizes the React-GA library to initialize Google Analytics with your tracking ID and track page views. The example uses useEffect hook to ensure the tracking code runs only once a component mount. You can use this as a foundation for implementing more advanced tracking features for your DApp. This brings us to the end of our presentation. Let's summarize it. This presentation has covered key strategies for improving DApp performance. We explored optimizing smart contracts for efficiency, enhancing front-end performance with techniques like caching and asynchronous operations, and leveraging real-time data handling for responsiveness. Now we'll open the floor for questions and clarifications. Feel free to ask about specific techniques, challenges you have encountered, and how to best apply these strategies in your own DApp development. Thank you and have a nice day.